Ravi, I guess we can start now. I've been told that humanities test is a bit long, so people might not show up.
Welcome everybody to the second student talk in our student talk series. Today we have with us Kartik Bhide, a BSMS fourth year physics major student and an aspiring computational physicist from IISER-TVM, speaking on machine learning and its applications in physics. He is currently working on a project with Dr. Tanmoy Mandal, where machine learning techniques are being employed in finding physics beyond the standard model. He has done several internships in the field of computational physics and will give us a brief glimpse into the same. Over to you, Karthik.
Okay, thank you for the introduction. Thanks to SITE for allowing me to do this talk. Okay, can you see the cursor if I move it on my screen? Yeah. Okay, great. Fine, so I'll start now. Before I begin, I just wanted to show two images. If you go to archive.org and search for machine learning, you get something like 82,000 articles. And if you filter that search to only the past 12 months, you get something like 36,000 results. So the point is that machine learning is a very trendy topic that lots of researchers are using in their work. Okay. So this is going to be what I'll talk about. I'll start with a very brief introduction to machine learning. Then I'll move on to two types of machine learning schemes which are used in the context of physics research. I'll explain what a typical workflow looks like in machine learning applications. Then a bit of math, and I promise it's only one equation. And then I'll just give some resources where someone who's interested can go and learn machine learning from. If there are any questions at any point, you can speak up or put it in the chat. I won't be able to see the chat, so just ask someone to speak up for you. Okay, so we'll start by asking the question, what is machine learning? Historically, ML, as it's called, was developed as a subfield of artificial intelligence. It draws on various mathematical and statistical concepts and is applied to data science problems. It is based on the fields of linear algebra, computer science, and statistics. So that is just the historical introduction to it. And now here's the crux of the matter. Very broadly speaking, machine learning is a collection of algorithms and tools used to extract meaningful information from data. And thus the hype is dead. Because if you boil it down to just the essentials, this is what machine learning is. Machine learning is used in situations where standard data science practices may not provide meaningful results, or the data is too complicated for classical techniques. So it's highly applicable for large data volume, highly correlated data, or when the dimension of the data is very high. By correlated, I mean that the data points are linked to each other, and by dimensionality, I mean the number of variables associated with each data point. Some real life applications from the industry include spam filters, video game bots, voice and facial recognition software, etc. Everyone knows about this. So that's all. This is my one slide brief introduction to machine learning. What I'm now going to move on is how we apply machine learning concepts in physics. So types of machine learning schemes. Machine learning is usually classified as supervised, unsupervised, and reinforced learning. If you go look at a textbook on machine learning, these are the three broad categories that you will find, and different tools of classes and algorithms will fall under these categories. We are not going to look at these categories in this talk. Rather, I'm going to talk about two schemes which are relevant to physics research. The first one is called classification, where the expected results are classes or groups of data. And the second one is regression, where the expected results are continuous functions of the variables of the data, or continuous at least in the computer science sense. So now you might have heard of the buzzwords, decision trees, K-clustering, neural networks. These are actually the tools that are used under the guidance of a scheme. So the analogy I like to use is that if your task is to go from city A to city B, you can choose to take a car or flight, bus, train, whatever. So in that sense, these are the tools that you will use to accomplish your task. For example, neural networks can be used in handwriting analysis, which is classification, or modeling and prediction, which is a problem of regression. So again, these are just the buzzwords, which are the tools. And what we are going to now look at is classification and regression. I'll start with classification, and I'll explain this with an example. So now suppose you have a crate of fruits which you want to classify. Now you know that there are three kinds of fruits in this crate: apples, oranges, and peaches. But you don't know individually which one is which. So without being able to tell which fruit is which, you perform measurements on the set of fruits and you tabulate your findings. So these are just some representative examples where you've gone and found the weight, the volume, the color, etc. of the individual fruits. So now what you do is you make a model based on inferences from the data, previous knowledge of fruits, and some amount of guesswork. So for example, you can say that an apple has weight between so and so, volume between so and so, same for the peach and orange. Again, based on the measurements that you have made, you can go ahead and define your model. So now that you have your model, you feed the data into the model and you allow it to make predictions. Based on how good or bad these predictions are, the model will be updated using machine learning algorithms. I'll explain what updating a model means, but in this context, it means changing the limits of how you have defined the weight and the volume. So for example, if you have an apple, but your model is calling it a peach, then maybe you need to change how you have defined your weight and volume limits. Again, I'll explain this in a later slide. So it's interesting to note that this example extends directly to particle physics, where the fruits are photons, electrons, hadrons, etc. And the variables are things like energy, momentum, and path of light. Okay, so that's it for classification. I'll now explain regression again in 2 slides. So now, ignoring the details, suppose you have measured the distance of an object orbiting a black hole over a long period of time. So now, as a first approximation, you can say it's a circular orbit, but it's probably elliptical or something governed by GR equations. So this is just an image that I made. On the x-axis, you have time. On the y-axis, you have distance from the black hole. The orange line represents the circular orbit, and the blue points are the data that you've measured. Now you can fit elliptical equations to the data that you have, and suppose that you find out that it doesn't exactly match the elliptical orbit, or it doesn't match what general relativity is predicting. Now, suppose you have found out that there's an other object in the system which is orbiting the black hole. This can explain the perturbed orbit, but what we don't know is the mass of the second object. So using GR, we can write down some equations with the variables being the masses of all 3 objects, and we will call this the model. Now the task is to estimate the masses of all 3 objects. What we do is we start by guessing the masses of the objects and see what the dynamics look like. If it's bad or if the dynamics are different from what the data is, we will recursively tweak the masses till we get a better fit of the data. Going back to the classification example, this is exactly the same as updating the model. Again, I'll explain this later. The message is that regression is essentially curve fitting on some level. It can be used to find a functional fit of the data, and this fit can be further used to extract information about the data. So in this example, fitting the observed data using GR equations gave us the masses. Now you might think that this is very easy and it probably can be done analytically, or at least using some software like Mathematica. Well, you're right, but this is a simple example. It is much more practical than standard techniques when the number of objects is very high. For example, galactic scale simulations. If you're familiar with general relativity, you might know that it's just a mess of coupled partial differential equations. So in those cases, using numerical techniques such as machine learning is beneficial. At this point, does anyone have any questions? Okay, I'll move on. I'll now show what the workflow looks like in a typical machine learning application. The most basic flowchart is this. You have some data and you want some information, and you're applying some machine learning algorithm in between. But it's not that easy. The first step is to split the data that you have into a training data set and a testing data set in a proportion of something like 80%, 20%. Why we do this, it'll be clear in the next slide. Now, you start with your training data and you feed it into the model. Based on the algorithm that you have, it's going to give you a prediction. The first time around, this prediction is not going to be good. So what you do is you have to update the model, like how we saw in classification and regression. You don't do it just once, you do it a bunch of times. With this number of times, you have to define by yourself. And once it has gone through all these cycles of updating the model, you have your final prediction. This is where the testing data comes in. Using the testing data, you validate your final prediction to get a final model. And once you have your final model, you can feed in new data and get research predictions. So this is what the code in a machine learning software looks like. I'll go through it once again. You feed your training data into the model, and it gives you a prediction based on the algorithm. The first time around, it's not going to be good, so you have to recursively update the model. Then you get a final prediction, which you validate using the testing data. You then get a final model into which you can feed your new data to get a research prediction. All right. Now, throughout this talk, I've sort of alluded to updating parameters. It's also referred to as optimizing the model. I'll now explain what that means with an example. Let us take the example of classification. Suppose you have some data that you know is classified as 0, 1, 1, 1, 0. Your model predicts 1, 0, 1, 1, 0 based on some variables. So how do we make this prediction better? As you can see, the first two data points are off, they're wrong. This is an example of binary classification. So what you do is, you start by defining something called the cost function, which is essentially the mean squared error of the prediction. And now this is where that one equation comes into picture. So this is what the cost function looks like. It's C is a function of the variables, and it is the squared difference between the data points di and the prediction pi. You sum over all data points and then you average it out. That's all. It's the mean squared error. Why is C a cost function of? Why is the cost function a function of the variables? Because if you change the variables, that means you're changing the model, which might give you a better prediction, which means decreased cost function. Now there is a hidden thing here, is that the prediction itself is a function of the variables. Pi is actually pi and then in brackets v1, v2. So that is why the cost function is a function of the variables. So at this point, I want to ask the audience two questions. One, so the first question, what is the cost function for this example here, where the data points are these and the model is this? Can anyone speak up or put it in the chat? It's not one, no. Okay, I guess I'll tell the answer then. So what you do is you take the first data points from the prediction. Yeah, Anup got it right, 0.4. Yeah, so you take 1 minus 0 whole squared plus 0 minus 1 whole squared plus 1 minus 1 whole squared, 1 minus 1 whole squared, 0 minus 0 whole squared. So that is 2. And then you have to divide by 5 because there are 5 data points. So the cost function here is 0.4. The second question I want to ask is, what does cost function equal to 0 mean? What does C is equal to 0 mean? Yeah, correct. Rohit got it right. Perfect fit. It means your prediction is exactly the same as the data. So now you can sort of guess what is happening over here. So the problem of better prediction has been reduced to a problem of minimizing the cost function with respect to the variables v1, v2, vn, because the cost function anyway was a function of the variables. So if we minimize the cost function, our prediction is becoming better. There are many ways to do this. The most basic method is called gradient descent. So recall that the gradient is a vector tangent to the surface of a function pointing in the direction of increase. So the negative gradient will follow the direction of decrease in the cost function. And here is just a diagram to show what I mean. So this is the cost function along the z-axis as a function of two variables, v1 and v2, on the x and y axes. So initially, with your first prediction, you started off at this point, very high on the cost function.
Hello?
Yes?
What are the bounds of this cost function C? Is it lies between 0 and 1?
No, nothing like that. No.
Okay.
It depends on the data.
It could be,
if you're even if you have just one data point, your model says 100, your actual data is 50, and the cost function is 50 squared. So there's no bounds on it.
Okay, it depends on the. Okay, thank you.
Yeah. So anyway, if the first time that your model gave a prediction, it starts off very high on the cost function, which means the cost function is very high. So what you do is you recursively follow the negative of the gradient along this cost function, and then eventually you will reach a point where the cost function is minimum. So this is what we mean by gradient descent. There are many algorithms to do this, and there's also different creative ways of executing the same algorithm. I'm not going to explain those. Once we reach the minimum, or more specifically, a local minimum of the cost function, then the variables have been altered in such a way that the model can make better predictions. So that is what I mean by updating the parameters or optimizing the model. This actually concludes my talk. Now I want to show two comics. I think John said he wanted an XKCD comic, which is exactly what you get, John. So on the left, the point being is that machine learning is just data analysis and linear algebra. And the second one is showing that machine learning is just statistics, but you put a frame around it to make it look pretty and attractive. Okay, so this is the end of my talk, and I will now give some resources where someone who is interested can learn machine learning from. So I suggest that you go ahead and learn Python, and the platform that I like to suggest to people is codeacademy.com. So why Python? Because it has a lot of modules and resources that people have already created, which you can use within a day for your machine learning applications. So you get it within Python, you get familiar with how to use external libraries, and especially Anaconda. If you don't know what that is, you'll find out eventually once you start learning Python. The book I want to suggest is Python Machine Learning by Sebastian Drashka. It has lots of examples, lots of code which is in the book itself, and it's very instructive. And you can generate data by yourself and apply machine learning to extract information from it. And there's always internships that you can go for. Yeah, this concludes my talk. If there's any questions, I can answer them to my fullest extent. Yeah, I guess I can share the slides, Akshita.
I have a question.
Yeah.
So like when you, in order to minimize the cost function, you would have to take a guess as to like what the model is going to be initially. Like given some variables, you would have to take a guess on the f of x sort of thing, like whether it's going to be a polynomial or a linear.
Yeah, you're right.
So how exactly would you do that? Like come to a conclusion on that?
Yeah, that's right. So what you're saying is that you don't know a priori what the cost function looks like. So you don't there's no graphical way of interpreting gradient descent. So there's actually numerical techniques for doing that. You start by defining a step with of magnitude something, and this step is what defines the change in the function in some direction. So there are certain algorithms for that. It's based on something called backpropagation, and it's essentially linear algebra. To add on to that, you start off by some random guess of the variables. And then once you have that random guess, then you start following the negative gradient to get to some point. Now it's possible that you reach the local minimum of the cost function. So what you do is you start with another random guess of the variables. and then you do this a bunch of times. Eventually, you might reach some model where the variables are such that you get the lowest possible cost function.
Okay, cool.
Are there any other questions?
Like, what do the usual functions look like? Are they like polynomial or stuff, linear or things like that, or
Do you mean the cost function?
not the cost function, the model you're predicting for the f of x?
Okay, for regression case.
Huh.
Yeah. So if you've ever seen a neural network diagram, there's actually a bunch of nodes on the left hand side. So if when you start with your data analysis, you can say, suppose it's a polynomial of some sort, of some degree. Then you say that your model is fx is equal to a naught x raised to 0 plus a1 x. You start by making a polynomial model. Then if your cost function is very high, if you don't like what you have, then you can go on to some other functional fits. You can try exponential, trigonometric functions. You can have a mix and match of all of these. So this is
Good.
it is up to the data scientist.
It's like a lot of guesswork, basically.
Yeah,
So
there is a lot of guesswork involved.
Okay, cool.
Do we have any more questions?
And, there was a question. Okay, two questions in the chat. Okay, Krishna Kumar, I'm a student, so please don't call me sir. Okay, how do we handle the physical interaction of particles and encode it in our algorithms? Okay, so in particle physics, the data that you have comes from the detector. Detectors actually measure a very small number of things in terms of momentum, mass. Mass you can infer, so that you're actually basically measuring momentum and energy. From these variables, you can infer stuff like mass, the charge, and things like that. So, and that is actually your data. You can also, from the detectors, you can figure out what the flight of path was, and again you can infer more information from this. So this is actually the data that you use, and because it's so most of the time in particle physics it's a classification problem, then each physics object that we call will have a certain momentum, energy, charge, flight of path associated with that. So then it's just a problem of classification. In fact, it is exactly like handwriting analysis. I hope I've answered your question. So John, could you expand a little more on applications in physics? I think, John, that is your area of expertise. But yeah, you can always go on archive and find things on your own. Machine learning is being used everywhere. I remember one time I was looking at new articles on archive, and something like 20 out of the 40 new submissions for the astrophysics section had machine learning in the title. So again, there's different techniques, classification, regression, and things like that. And once you figure out a problem where you want to apply these things, then the world is your oyster. Yeah, so John works on machine learning and quantum computation. That is also somewhere where machine learning is applicable.
Any more questions? So if there are no more questions, I guess we can bring this session to a close. Thank you so much, Kartik, for coming here and giving us such an informative talk. It's nice to
Thanks.
see what's actually behind all the buzzwords about ML and AI in a much more, cold light of data analysis and mathematics. Thank you everyone for coming. Please make sure to follow Sai on all the platforms and to stay updated and connected about all these events that we organize. Now, if anyone else wants to give a talk, just mail us at site@isertvm.ac.in, or preferably just message us on our social handles on Insta or WhatsApp. So stay tuned for more talks, and we'll see you later, I guess. Thank you once again.
Yeah, thanks for having me.